This is chemical energetics. And in this unit, I'm going to describe what is happening to energy during a chemical reaction. Now, everything that we know is made out of chemicals. This here, this here, all this, this is a big glob of chemicals. This board here is a chemical. The air, that's full of chemicals, yeah? So chemicals are like matter, which is something you can see like this. And energy, yeah, the energy allows me to do this, like become a Kung Fu master. But what we're really interested in is the study of energy during a chemical reaction. Now, in a chemical reaction, particles are rearranged to form new particles. Like here we have 3 particles, they break up, they collide, and they form new particles. Alright? And in this particle, this here is what we call a chemical change. But in every chemical reaction, there is an associated heat energy change that is on it. And it's not illustrated here. But I'm going to just go down to see how we describe this heat energy change during a course of a reaction. Alright, to do that, we need to draw what we call an energy profile. Here we go. An energy profile is made out of the x-axis and a y-axis. On the x-axis is what is happening during the course of the reaction, the time it takes for the reaction to get from a reactant to a product. Now, on the y-axis is the energy content level, and it can be measured in joules or kilojoules. All right, joules. Now let me write that down. Joules. Yeah, that's the unit for energy. So I'm going to give 2 examples of how these energy profiles can be drawn in a simple manner. First example, I'm going to mix hydrogen bicarbonate into an acid. Here we have the particles inside and the solution, which forms the environment, and a thermometer that measures the heat, or the temperature, not the heat. For temperatures, thermometers can measure heat. Yeah, okay, so when we put hydrogen bicarbonate, when we have hydrogen bicarbonate and acid, it has an energy content level of this. Now, we're not going to be concerned about the exact numbers, because what I want you to get is the concept behind it. So, it has an energy level here. And when you drop the hydrogen bicarbonate into the acid reaction vessel, and you stir it, what you see is that the temperature in the thermometer will go down. It decreases. What is happening there? That means the energy in the environment is going into the products. And when energy goes into the product, that means that the energy content level of the products have increased during the course of the reaction. And this here is what we call an endothermic reaction, where heat is being absorbed into the particles and into the product. So in an endothermic reaction, the energy content in the reactants are lower than the energy content of the products. Another example is when we put magnesium ribbon into an acid bath. So when we have magnesium and hydrochloric acid, the energy content is around here at the start, at the beginning of the reaction. And when we drop the magnesium ribbon into the acid bath, what we will see is some fizzing and bubbling occur, and when you will also see that the temperature on a thermometer will go up, and the reaction vessel gets a little hot. What is happening is that the energy content in those reactors are escaping from the particles and going into the environment. So that means that the energy content of the products is lower than the energy content of the reactants. This means that this reaction is an exothermic reaction. An exothermic reaction is when the energy content of the reactants are higher than the energy content of the products. These energy contents now are described as the change of energy, heat energy, the change of heat energy. And this change of heat energy is called the enthalpy change, and is used, and physicists and chemists and even biologists scientists will use the symbol delta H to describe enthalpy change, which is the change in heat energy during the course of the reaction. The units for enthalpy change is kilojoules per mole. All right. So this is kind of an easy energy profile. But remember, when you have particles floating around here, what will cause it to break apart? What will cause the bonds to break apart? Something external has to come in to cause the bonds to break apart. And this external stimulus is energy. And when energy is introduced in the form of heat or light, the bonds of these particles will break. They will randomly collide and form new bonds if it's favorable, and form new products if that energy state is favorable. Okay? And when they form new particles, energy is also released. So, if energy is introduced here and released here, then this profile here doesn't really quite make sense anymore. And that is what we're going to do for next period, is to study how these energy profiles should actually look like when we take into consideration of what energy that is needed to break those bonds, and when energy that is released when these bonds are reformed.